From Luna 1 to Artemis, mapping 12 key milestones in lunar exploration history. Introduction. The exploration of the Moon has been a remarkable journey that began in the late 1950s and has evolved dramatically over the decades. This report outlines 12 pivotal milestones in lunar exploration history, from the first robotic missions to the highly anticipated Artemis program, highlighting the technological advancements, scientific discoveries, and international collaborations that have shaped our understanding of Earth's closest celestial neighbor. 1. Early robotic missions 1959 to 1966. The Soviet Union pioneered lunar exploration with Luna 1, launched on January 2, 1959, marking the first spacecraft to reach the Moon, albeit as a flyby. This was soon followed by Luna 3 on October 4, 1959, which captured the first images of the Moon's far side, revealing significant geological differences from the near side. In response, the United States initiated the Ranger program, with Ranger 7 successfully transmitting detailed photographs of the lunar surface on July 28. 1964, the era culminated with Luna 9, which on January 31, 1966 became the first spacecraft to achieve a soft landing on the Moon, providing vital data about the lunar surface characterized by powdery soil and rocky debris. 2. The Apollo program 1968 to 1972. The Apollo program marked a watershed moment in lunar exploration. Apollo 8, launched in December 1968, was the first crewed mission to orbit the Moon, allowing astronauts to observe and photograph the lunar surface from a new perspective. The pinnacle of this program, Apollo 11, achieved the first crewed landing on July 20, 1969, when Neil Armstrong and Buzz Aldrin set foot on the Moon, famously declaring, "That's one small step for a man, one giant leap for mankind." The Apollo missions returned a total of 842 pounds of lunar samples to Earth and conducted extensive scientific experiments, revolutionizing our understanding of lunar geology. Subsequent missions, including Apollo 15, 16, and 17, incorporated lunar rovers and extended stays, further enriching our knowledge of the Moon's composition and history. 3. Post-Apollo robotic missions 1994 to 1999. After the Apollo program, lunar exploration took a backseat until the 1990s, when robotic missions resumed with Clementine 1994 and Lunar Prospector 1998. Clementine mapped the lunar surface and detected signs of water ice in permanently shadowed regions at the poles, while Lunar Prospector confirmed hydrogen presence, suggesting the potential for water resources on the Moon. 4. Emergence of international efforts 2000s. The 21st century saw a resurgence of global interest in lunar exploration. Notable missions included Kaguya 2007 from Japan, which provided high-resolution mapping and data on the Moon's topography, and Chandrayaan 1 2008 from India, which discovered water molecules on the lunar surface. These missions demonstrated a shift towards international cooperation and knowledge-sharing in space exploration. 5. Recent missions and future plans 2020s. The recent decade has been marked by significant lunar missions such as China's Chang'e 5 2020, which successfully returned lunar samples to Earth, and India's Chandrayaan 3 2023, which landed near the Moon's south pole, continuing the exploration of lunar geology. Looking ahead, NASA's Artemis program, set to begin with Artemis I in late 2021, aims to land humans on the Moon by the mid-2020s. Establishing a sustainable presence and setting the stage for future Mars missions. Timeline of key events. Year, mission/event, description. 1959, Luna 1, a first spacecraft to reach the Moon. 1959, Luna 3 captured first images of the Moon's far side. 1966, Luna 9, a first soft landing on the Moon. 1968, Apollo 8, first crewed mission to orbit the Moon. 1969, Apollo 11, first crewed landing on the Moon. 1972, Apollo 17, last crewed mission to the Moon. 1994, a Clementine mapped the Moon and hinted at water ice presence. 1998, Lunar Prospector confirmed hydrogen presence at lunar poles.
2007 Kaguya high-resolution mapping of the Moon. 2020 Chang'e 5 returned lunar samples to Earth. 2023 Chandrayaan-3 continued lunar exploration efforts. 2024 Artemis I first mission of the Artemis program. Conclusion. The exploration of the Moon has come a long way from the early robotic missions of the late 1950s to the ambitious Artemis program aimed at establishing a sustainable human presence on the lunar surface. Each mission has contributed to our understanding of the Moon, paving the way for future exploration and the potential for life beyond Earth. As we look forward to the next chapter in lunar exploration, the lessons learned from past missions will undoubtedly guide our endeavors in the cosmos. The content presents a detailed historical account of lunar exploration, highlighting key milestones from the first robotic missions to future human exploration plans under NASA's Artemis program. Here are some counterintuitive pieces of information derived from the content. 1. Early robotic missions set the stage for human exploration. While it may seem intuitive that human missions naturally follow robotic ones, the reality is that early robotic missions were crucial not just for gathering data but also for shaping the strategy and technology for human landings. For example, the Luna 9 soft landing provided essential information about the Moon's surface that was vital for the Apollo missions. 2. The Apollo missions were not just political statements. The Apollo program is often viewed through a lens of national pride and competition during the Cold War. However, the scientific outcomes of these missions were profound. The data gathered reshaped our understanding of planetary science and the history of the solar system, showing that exploration can yield unexpectedly significant scientific insights beyond mere geopolitical goals. 3. Clementine and Lunar Prospector identified water ice before later missions. Although the presence of water ice on the Moon has become a more widely acknowledged goal in recent lunar exploration narratives, early missions like Clementine hinted at its existence in permanently shadowed regions. Despite this, the significance of these findings was not fully recognized until much later, demonstrating that initial discoveries can sometimes be overshadowed by subsequent narratives. 4. The misconception of the Moon's surface conditions. Initial perceptions of the Moon, particularly after Apollo, suggested it was barren and lifeless. However, discoveries such as those from Apollo missions indicated a more complex geological history, including volcanic activity and a variety of surface materials. This challenges the simplistic view of the Moon as an inert body, revealing it as an active participant in solar system history. 5. Lunar meteorites provide complementary data to sample returns. Many might assume that only samples returned from the Moon, such as those from Apollo missions, are valuable. However, lunar meteorites found on Earth have provided additional insights and complementary data that enhance our understanding of lunar geology. This suggests that valuable scientific data can come from unexpected sources and not just from direct missions. 6. The role of international collaboration in lunar exploration. While the US and the Soviet Union dominated early lunar exploration narratives, the modern landscape is characterized by international collaboration. This shift underscores that space exploration is increasingly seen as a global endeavor rather than a competitive race, countering the historical perspective that framed it as a zero-sum game. 7. The importance of non-crewed missions. It might be assumed that crewed missions are inherently more critical to the success of lunar exploration. However, the early non-crewed missions provided the foundational knowledge necessary for safe human landings and have continued to play a vital role in ongoing exploration efforts. 8. Misleading simplicity of the timeline. The summary presents a linear progression of lunar exploration, but in reality, the development of space exploration technology and scientific understanding has often been non-linear and fraught with setbacks and unexpected discoveries. This complexity challenges the notion that progress in science is always straightforward and predictable. 9. Lunar exploration's impact on Earth science. The implications of lunar exploration might seem confined to our understanding of the Moon and its geology. In contrast, the exploration has provided insights into Earth's geological history and planetary formation processes, revealing unexpected connections between lunar studies and terrestrial science.
10. Future missions are not just about human presence. The Artemis program is often framed as a return to human lunar exploration. But its goals extend beyond just landing humans on the moon again. The program aims to establish a sustainable presence and serve as a stepping stone for future Mars missions, indicating a broader vision for human space exploration that includes long-term habitation and resource utilization. These counterintuitive insights highlight the complex and often surprising nature of lunar exploration history, revealing that our understanding of the moon and its significance continues to evolve with each mission. The exploration of the moon has been a remarkable journey marked by numerous milestones that detail not only the technological advancements in space exploration but also the evolving understanding of our celestial neighbor. While the history of lunar exploration is often highlighted for its notable missions, several important aspects are frequently overlooked, yet they hold significance in understanding broader themes in science technology.
And international collaboration. 1. Robotic precursor missions, foundation for human exploration.
The early robotic missions, particularly those by the Soviet Union, were pivotal in setting the stage for human exploration.
Luna 1 and Luna 3 provided foundational data about the moon's environment.
However, the significance of these missions extends beyond mere data collection. They showcased the capabilities of robotic technology and the necessity of such missions in reducing risks associated with human landings.
The successful soft landing of Luna 9 in 1966, while a technical achievement, also highlighted the importance of understanding the lunar surface's physical properties, which was crucial for subsequent crewed missions. This foundational role of robotics is often overshadowed by the glamour of the Apollo missions, yet it underscores a systematic approach to exploration that balances human ambition with technical preparedness. 2. The role of international collaboration. As we transitioned into the 21st century, the landscape of lunar exploration began to reflect a shift toward international collaboration.
Missions like Japan's Kaguya Selene and India's Chandrayaan-1 marked a significant departure from the Cold War competition, indicating a more unified approach to space exploration. The significance of such collaborations lies in the shared knowledge and resources they foster, which can lead to more efficient exploration efforts and a broader understanding of the moon. This shift is essential not only for lunar science but also for establishing frameworks for future international endeavors, including Mars exploration and beyond.
Many reports gloss over this aspect, yet international cooperation is increasingly vital in addressing the complex challenges of space exploration, including planetary defense, resource sharing, and scientific collaboration. 3. Scientific discoveries from robotic missions. Missions like Clementine and Lunar Prospector in the 1990s provided critical insights into the moon's composition and environment,
particularly regarding the potential presence of water ice in permanently shadowed regions. The significance of these discoveries cannot be overstated. They have implications for future crewed missions, as water is essential for sustaining human life. The hint of water ice near the lunar poles presents opportunities for in-situ resource utilization, a concept often discussed but underappreciated in mission planning. The ability to use lunar resources could drastically alter the logistics of lunar exploration, allowing for longer missions and potentially paving the way for a sustainable human presence on the moon. 4. The cultural and historical context of lunar exploration. The narrative of lunar exploration is often viewed through a purely scientific or technological lens, but the cultural and historical contexts are equally important. The Apollo missions, for example,
were not just scientific endeavors, they were also political statements during a time of intense global competition and domestic turmoil in the United States.
The cultural impact of the moon landings, including the iconic images of astronauts walking on the lunar surface, shaped public perception of space exploration and inspired generations. Understanding these cultural contexts can provide insights into how space exploration is perceived and prioritized by societies, which is critical for garnering public support and funding for future missions.
5. The evolution of lunar geology understanding. The Apollo program fundamentally altered our understanding of lunar geology, revealing complex processes that shaped the Moon's surface. However, the significance of these findings extends beyond the Moon itself. The geological processes observed on the Moon, such as impact cratering and volcanism, are applicable to other bodies in the solar system, including Earth.
The lessons learned from lunar geology have implications for understanding planetary formation and evolution more broadly, yet this connection is often underexplored in discussions of lunar missions. Recognizing this interconnectivity enriches our understanding of planetary science and informs future exploration strategies for other celestial bodies. 6. The future of lunar exploration, Artemis and beyond. While the Artemis program is frequently covered in terms of its goals to return humans to the Moon and establish a sustainable presence, the broader implications of this initiative are often overlooked. Artemis represents not just a return to the Moon but a potential stepping stone for further exploration of Mars and beyond. The technologies developed and lessons learned from Artemis missions will likely inform future interplanetary travel and habitation efforts. Additionally, the focus on sustainable exploration emphasizes the importance of long-term planning in space exploration, a critical factor that can influence the success of future missions. Conclusion. The history of lunar exploration is rich with milestones that collectively illustrate humanity's quest to understand our place in the universe. However, key aspects such as the foundational role of robotic missions, the importance of international collaboration, the implications of scientific discoveries, the cultural context, the evolution of geological understanding, and the strategic vision for future exploration are often underappreciated. Recognizing these elements not only enhances our understanding of lunar exploration but also informs our approach to future endeavors in space, ultimately shaping humanity's journey beyond Earth. 1. The evolution of robotic missions. The exploration of the Moon began with early robotic missions, starting with the Soviet Luna 1 in 1959, which marked the first successful flyby. This initial phase included important milestones such as Luna 3, which captured the first images of the Moon's far side, and the U.S. Ranger missions that provided detailed photographs of the lunar surface. The significance of these robotic missions lies in their foundational role in gathering critical data that would inform subsequent human exploration. They not only mapped the Moon's surface and identified potential landing sites but also provided insights into the Moon's geological composition, paving the way for the Apollo program. 2. The Apollo program's transformative impact. The Apollo program, particularly Apollo 11's crewed landing in 1969, represents a monumental achievement in human space exploration. This program fundamentally changed our understanding of lunar geology, enabling scientists to study samples returned from the Moon and leading to significant revelations about the Moon's history and formation. The Apollo missions demonstrated the feasibility of human space travel to other celestial bodies and inspired future generations to pursue careers in science and engineering. The program's scientific contributions continue to influence planetary science and geology today. 3. International collaboration in lunar exploration. The early 21st century has witnessed a marked increase in international cooperation in lunar exploration. Missions from countries such as China, India, and Japan have added to a growing body of knowledge about the Moon, highlighting its geographic and mineralogical diversity. This collaborative approach not only enhances scientific research but also fosters diplomatic relationships between nations. The Artemis program, which aims to return humans to the Moon and establish a sustainable presence, exemplifies the trend of international partnerships in space exploration, as it invites contributions from various countries and private entities. For future prospects in the Artemis program signifies a new era of lunar exploration with ambitious goals that extend beyond mere visitation. It aims to establish a sustainable human presence on the Moon by the mid-2020s, using the Moon as a stepping stone for future missions to Mars and beyond. The program's focus on lunar resource utilization, including the potential for extracting water ice, reflects a strategic approach to long-term space exploration. This forward-looking initiative emphasizes the importance of returning to the Moon not just for exploration but for practical applications that could support human life on other planets. The lessons learned from Artemis will be crucial for humanity's continued exploration of the solar system. 1. Voyager Program 1977. The Voyager missions launched by NASA in 1977 were designed for long-term exploration of the outer planets. But they also provided incredible insights into the solar system, including the Moon. Voyager 1 and Voyager 2 conducted flybys of the gas giants and their moons, capturing detailed images and data that enhanced our understanding of planetary atmospheres, magnetic fields, and geology. Key milestones included the discovery of active volcanism on Jupiter's moon Io and the complex ring systems around Saturn. The data returned by Voyager significantly advanced planetary science and set the stage for future exploration. 2. Mars Exploration Rovers 2004 onwards. The launch of the Mars Exploration Rover Spirit and Opportunity marked a significant milestone in planetary exploration. These rovers were designed to explore the Martian surface, conducting detailed geological analyses and searching for signs of past water presence. The findings from both rovers transformed our understanding of Mars' history and its potential to support life. The successful deployment and operation of these rovers also demonstrated the viability of robotic exploration on other celestial bodies, paving the way for future missions, including those targeting the Moon and beyond. 3. Hubble Space Telescope 1990. Launched in 1990, the Hubble Space Telescope has revolutionized our understanding of the universe, providing deep insights into celestial phenomena, including the Moon and other bodies in our solar system. Hubble's ability to capture high-resolution images of the Moon's surface and its transient phenomena has complemented lunar exploration missions, aiding in the study of lunar geology and atmosphere. The telescope has provided invaluable data on the Moon's influence on Earth and its role in the solar system's dynamic processes, contributing to our broader understanding of planetary science and astrophysics. Future outlook. Predictions for lunar exploration. The history of lunar exploration has laid a robust foundation for future endeavors. As we shift our focus towards the next phase of discovering and utilizing the Moon, several key predictions can be made about the future of lunar exploration, especially with the anticipated Artemis program and the broader international collaboration in space. 1. Human presence on the Moon. By the late 2020s, we will likely see a sustained human presence on the Moon through NASA's Artemis program. This initiative aims to establish the Lunar Gateway, a space station in lunar orbit, and facilitate regular crewed missions to the lunar surface. Much like the International Space Station (ISS), these missions will focus on both scientific research and the development of technologies for future Mars missions. 2. International collaboration. The future of lunar exploration will be characterized by unprecedented international collaboration. Countries like China, India, and Japan are expected to play significant roles alongside the US in lunar exploration. This collaboration will extend to shared missions, joint research, and the pooling of resources to achieve common goals such as sustainable lunar exploration and potential colonization efforts. 3. Commercial lunar activities. The rise of private space companies will greatly influence lunar exploration. By the 2030s, we can expect commercial lunar landers and rovers from companies like SpaceX, Blue Origin, and Robotic to actively participate in lunar missions. These commercial entities will not only support government missions but also conduct their own explorations for mining resources, including water ice and rare minerals. For utilization of lunar resources, the Moon is rich in resources that can be utilized for both lunar and Earth applications. The discovery of water ice in permanently shadowed regions means that the Moon could serve as a refueling station for deeper space missions. By the 2030s, technologies for extracting and processing these resources will likely be developed and implemented, paving the way for a sustainable human presence. 5. Scientific advancements. Future lunar missions will continue to yield significant scientific discoveries. With new missions planned for the lunar poles and far side, scientists will gain unprecedented insights into the moon's geology, history, and potential for past life. Additionally, these missions will advance our understanding of planetary formation and evolution, contributing to broader scientific knowledge applicable to other celestial bodies. 6. Technological innovations. The challenges of lunar exploration will spur technological advancements in robotics, life support systems, and habitat construction. Innovations developed for the moon, such as advanced habitats and in situ resource utilization (ISRU) technologies, will eventually be adapted for Mars missions and other deep space explorations, enhancing our capabilities for human habitation on other planets. 7. Preparing for Mars. The moon will serve as a critical testing ground for technologies and strategies needed for human missions to Mars. By the late 2030s, lessons learned from lunar exploration will be directly applied to Mars missions, including habitat construction, resource utilization, and crewed mission logistics. The moon's proximity to Earth makes it an ideal location for testing and refining the technologies that will ultimately be used on Mars. 8. Educational and inspirational value. As lunar exploration continues, it will inspire a new generation of scientists, engineers, and explorers. Educational programs focusing on STEM, science, technology, engineering, and mathematics will incorporate lunar exploration, fostering interest and engagement in space sciences among young people worldwide. 9. Space policy and governance. The expansion of lunar exploration will necessitate the development of international space policies and governance frameworks. By the 2030s, discussions surrounding the ethical use of lunar resources, the preservation of lunar heritage sites, and the regulation of commercial activities will likely be at the forefront of international space policy. 10. Sustainable lunar bases. By 2040, there is potential for the establishment of permanent lunar bases that support research, exploration, and commercial activities. These bases will incorporate sustainable living practices, utilizing local resources for construction, energy, and life support systems, creating a viable model for future off-world colonies. 11. Public engagement and global participation. The future of lunar exploration will increasingly involve the global public in various capacities, including citizen science projects and public-private partnerships. This engagement will create a sense of shared ownership and responsibility for space exploration, encouraging global participation in future missions. 12. Cultural and philosophical implications. As humanity re-establishes its presence on the moon, deeper philosophical questions about our relationship with space, the preservation of celestial bodies, and the ethical implications of colonization will emerge. Ongoing discussions will shape how we view our place in the universe and the responsibilities we hold towards other celestial bodies. In conclusion, the future of lunar exploration is poised for significant advancements driven by international collaboration, technological innovation, and a focus on sustainability. The moon will not only serve as a stepping stone for human exploration of Mars and beyond, but will also inspire and engage the global community in the quest for knowledge and understanding of our place in the cosmos.